It's math o'clock with Mr. Barnes. It's Mr. Barnes o'clock. Let's learn some math with Mr. Barnes. Let's Mr. Barnes some math.
Go math!
What is inverse variation? Let's define it with an example. Let's say you wanted to throw a cupcake party, as you do, and you made 24 cupcakes, and you wanted to divide them evenly for all your friends. Now, they have to be make sure that you're dividing evenly. If you give one person 2 cupcakes, another person 5 cupcakes, that's how fighting starts. But you want to divide it evenly using the operation of division. Let's start by defining some variables. We're going to let x equal the number of guests. Now it's a variable. I don't know if your friends are like my friends, but sometimes friends say they're going to show up to your cupcake party, and then they don't show up. And sometimes you have friends say, oh, I can't make the cupcake party, and then they do show up. And sometimes I have friends say, I'll try to squeeze in your cupcake party in between 2 other cupcake parties you're going to go to. Just tell me yes or no, people. But anyway, it's a variable. So we're going to take those 24 cupcakes and divide it by the number of guests, whatever that happens to be. And that's going to give me my amount of cupcakes per person. Now let's imagine a couple of scenarios. Let's imagine let's make a tea table here. What if you have just one person at the cupcake party? I can imagine what that would be like.
Where is it?
Well, not much of a party, but you get the idea. What if you had 2 people at a party? How many cupcakes would that be? Hey, great party! Oh, 24 cupcakes. You want to split these between the 2 of us?
No.
Pretty good party. If I had 3 people, we'd each have to share 8 cupcakes. If I had 4 people, we'd share 6. If I had 5 people, we'd have to get out the butter knife and divide things into fifths. We'd each get 4 and 4/5 of a cup. I can't write like that. Let's say 4.8, shall we? Which is fine. 4.8 cupcakes is more than enough sugar for a person. All down to if I had 24 people, I'd have 1 cupcake per person. That seems pretty reasonable. If I had 48 guests, we'd all have to say, all right, everybody gets half of a cupcake, and on down the line. If I had, let's say, 24,000 people that seem to show up. Have you ever seen one of those movies where everybody invites a friend over, and they all invite people over from cupcakes party, and everybody to drink cupcakes, but they would only get little crumbs. They get tiny little crumbs. It would work. So it would be a graph that looks like this. As x increases, y approaches 0. Now, it would be impossible to have 0 people at this party. You can't divide by 0. So that's going to be an asymptote going the other way. It doesn't. The model kind of breaks down as x could never be half of a person. It would only work with integers. But you get the idea. You see this beautiful rational curve that you're going to be graphing in the next section. So what is inverse variation? Well, the problems you're going to be solving on delta math are pretty dry, truth be told. If p and q vary inversely, and p is 22 and q is 18, determine q when p is equal to 12. This type of problem, without any real-world scenarios like cupcakes or friends, makes my head spin a little bit. But as long as you look at these words, vary inversely, you can determine the equation that you should use. P varies inversely with q. So we have some constant here that we don't know, but we know that if we divide it by q, we're going to get p. There's no addition or subtraction signs for inverse variation. It's always this simple format. You're taking some number, dividing it by an input. In this case, we use q, and then we're going to get p. So let's find out what k is. We have one ordered pair here when p is 22 and q is 18. And if we multiply both sides by 18, we'll get 396 equals k. So this is the number that we're dividing by Q. And now, when you have inverse variation, you can actually switch these. I had a moment where I was looking at this, and I realized really the input should be P here, and Q should be the output. This will work out the same, but since X comes before Y, it probably makes a little more sense to make this P and this Q. Either way, it'll work. Inverse variation, you can actually switch these variables and get the same outcome. But since we know K is 396, I'm not going to switch up the variables for here. I'll just keep trucking along this path. This is our function, is P is equal to 396 equals Q, and we can actually, if you prefer, we can use this as well. This is equivalent. You can prove that using algebra. And this will come up to play in a little bit here, because we want to determine Q when P is equal to 12. So I'm going to plug in 12 in for P, and then we're going to solve for Q. I'll multiply both sides by Q. By the way, Q cannot equal 0. Keeping in theme with this chapter, you cannot divide by 0. And then I get a relatively simple problem. I'm going to divide both sides by 12. I don't know where my calculator at this moment is, and it probably would just save you a little bit of time. 33, that can't be right. 33. It is right. So this would be my answer. And we did that in 2 steps, finding K and finding Q. And it's the same pattern every time. So once you get it down, it's not so bad. I think there's some alternate examples where it's P varies inversely with the square of Q. That's not too much harder. You just stick a little exponent on there. It's not so bad. So good luck. We're going to be looking at those beautiful rational curves in a little bit. But I think that should get you started with the idea of inverse variation.